Welcome to Fluid Mechanics Notes for ENME 331, Introductory Course in Fluid Mechanics. Today we're going to be talking about some quantities related to the kinematics of fluids, or how they move, namely streamlines. This is followed by part 2 and 3 on streaklines and pathlines. So let's get started in. I want to show you a little animation, which is shown here. This is a numerical simulation that's running on my iPad, solving the equations of motion for a fluid for flowing around a cylinder. This is a very common prototypical flow. We have a uniform upstream conditions on the left-hand side, and the fluid's moving from left to right. The cylinder is making it move around it, it speeds up, and then downstream we see a very unsteady wake. What we're plotting in here, we see these small little colored line segments. These are velocity vectors, the color indicating the velocity magnitude and the orientation of the segment showing the direction that the flow is going. As we talked about earlier, this is a Lagrangian velocity field. And then we're also showing on top of that some smoke lines that are being released upstream off the left-hand side. And every once in a while a thick blob of smoke comes in to sort of give us a time reference point. Now the question is, are these what we're looking at? Do these represent the streamlines of the flow? And that's what we'll try and answer here at the end of the problem, and also talk about some of the ramifications. Streamlines are actually the most important of these three lines that we're talking about, but some of the other quantities are easier to generate. Alright, so a definition for a streamline is simply a curve which is everywhere tangent to the local instantaneous velocity field. Okay, so now these are some very important keywords here. It's a curve everywhere tangent to the instantaneous velocity field. So what that implies is we're talking about at one instant in time. And these curves can look different at different instants in times if we happen to have an unsteady flow, as what we'll see here in just a second. So this represents the direction of the flow at any given instant, and that's why they're such a useful quantity to have a look at. Well, now let's talk about how to calculate this analytically. Here I'm going to show schematically just an arbitrary velocity field. This may be a stagnating flow here, velocity coming down from the top and hitting a plane and moving off to the right, as we see here. And these vectors are showing us the velocity at different points in the flow field. Now we're going to want to draw a streamline here at a fixed instant in time. And so at that instant of time, let's call it t, it's going to pass through a point of our choosing that we're going to call x0 and y0. And so let's say that that's this location right here, x0 and y0. And I've drawn the velocity vector that's shown here now. I've highlighted in blue. It has two velocity components in the horizontal and vertical direction. And if we zoom in on that, we're going to take the horizontal component to be u and the vertical component to be v. And we see that the curve that we want to draw has to just be parallel to that velocity vector at that location. So the slope that I'm showing here is going to, of that curve, shown here in red, is going to lie exactly parallel to that vector. Well, the slope of that vector is just simply given by the ratio of these two velocity components. The rise is given by v and the relative run is given by u. And that's going to have to then correspond to the rate of change, or the slope of the curve, dy dx. So the relationship that we're looking for to draw a streamline is going to give by this. dy dx is equal to v divided by u. Now this is true for the only equation you need for a two-dimensional flow such as the one I've drawn here, but if it's a 3D Cartesian flow, we'd need two more equations, and this would be given by, you could say dy dz is equal to v over w, where w is the the z component of the velocity, and then lastly you'd need another one, dx dz is equal to u over w. Now these three equations then would have to be solved simultaneously, In general, you'd probably have to integrate them numerically to get the answer as a simultaneous set of ODEs, but in some cases, particular 2D flows, you may be able to integrate this first equation analytically if it's a separable equation. So let me give you an example of that here on this next page. Okay. So let's have a sample flow here where u is given by constant a divided by 1 plus t, and the vertical velocity component is given by b times t squared. So these two quantities here are constants. Okay, so let's go ahead then and apply the equation of interest. And remember, this is going to be at a given instant t, so t is known. We assume t is given. And we want it through the point x naught and y naught. All right, so let's take our definition here that we had for a streamline, namely dy dx is equal to v divided by u. And if I now simply plug in for v, I'm going to have here b times t squared for v. I plug in for u, this is going to be a divided by 1 plus t, or in other words, that's equal to b divided by a times t squared times 1 plus t. Now, hopefully I haven't gone too far to the right there. So we can now, let's multiply this through by dx, right? So this multiplied by dx, multiply that by dx. This becomes equal to simply dy on the left. And then on the right, this is going to be equal to b divided by a t squared 1 plus t times dx. And now we're going to integrate this over our dependent variable here. We're going to start dy, we're going to start at our given position y naught and end at position y. And this integral, we're going to start at position x naught as our initial position and finish at some position x, wherever that takes us. And now in completing this integral, what we see is that the left-hand side is, of course, very simple, y minus y naught. And what we notice on the right-hand side is that b over a and t are constants with respect to x. So we can write this as b divided by a, t squared 1 plus t, just comes outside of our integral, and then we're left with simply x minus x naught. All right, so our question is, what does this look like? Well, it's a pretty simple function. It's actually a linear function, y and x with no complicated dependence. And as we said before, this is all a constant. And this constant then represents the slope of our line. But all of our streamlines are straight lines. Now this is, of course, specific just to this one example. They don't have to be straight lines. But if we now look at this set of streamlines as a function of time, here's what we get. Here I've drawn the velocity field with green arrows, and we see as time goes on, the u component shrinks and the v component grows, and so the velocity vectors tilt rapidly upward. The streamlines here are straight lines. They're everywhere tangent to the curve, and if we stop this at any point, that we'd see that they are always parallel everywhere. This is a very simple quasi one-dimensional flow. At any instant in time, all of the values are constant with respect to space. All right, so let's go ahead and look at a more complicated flow. Let's go back to a snapshot of that flow around our cylinder. And what we see here is we could draw some streamlines in this figure. Let's go ahead and try and do that. I'll do that with this yellow ink here. Let me start at a point up here. It's relatively straight, and everywhere I go, I'm going to try and interpolate and draw the curve so that it's tangent to what I think the velocity vector is at that point. And what we see is I go through here, I move, I'm going tangent to these velocity vectors, going around and through and down. Okay, so there's one. Let me move to another part a little bit lower. Let's start here. As I go in, I kind of I go around the cylinder, and then there's a little bit of a jog around in here. I come down, I get caught up in this eddy back here. Whoops. And this comes up through here, and I'm locally trying to stay tangent to these velocity vectors. Let's take one just to finish down here on the bottom. So we can see that those smoke lines that are in here and those with those blobs on it were not at all streamlines, not in any general sense anyway. Here you can see I'm crossing over these smoke lines back here, and they're not coinciding. Up here, upstream of the cylinder, however, they do tend to follow these smoke lines. And as we go along here, I think those are kind of the same, and then they sort of deviate here. So somewhere around this point forward, at this instant, they seem reasonably close, but downstream, all bets are off. So those smoke lines are definitely not streamlines. One last example for this, and then I'll sign off. Here's another flow that has time-varying streamlines in it. So this is an unsteady flow of a downward-facing jet. So up here in the flow, there is a jet of air blasting down, and there is what's called a shear layer here, and a vortex forms like a little tornado that rolls up. Very intense, tracking along down there, and you can see the velocity magnitude here in the background. This is in meters per second over here. So this is a region, this red region is close to 30 meters per second. That's quite fast. That's probably about like 80 miles an hour. And then out here it's much slower. And we see the strong rotational region as these streamlines are spinning around. And everywhere these curves are tangent to the instantaneous velocity field. Okay, thank you very much. That's Streamlines.